Well, good morning, everybody. So today's going to be a little bit different. For the weeks that we've been in online school, the videos that you've been watching have actually been unedited videos that we've recorded, obviously, of classes from last year, and then we've just been posting these videos. Well, the material that we're going to cover today actually doesn't lend itself well to that because the majority of what we would be doing would actually be done in class. And in order to really understand this, you would need to be able to see the demonstrations that we use in order to teach this concept of chemical equilibrium. So what we've decided to do is actually, thanks to a teacher named Kevin Dirksen at Egan High School, we've actually taken his demonstration, which is a little different, but fairly similar to the one that we use in class. And we're going to use his YouTube resource as a rallying point as we talk through the idea of chemical equilibrium. I think we'll find that this will work well, and we're going to dig in and talk about chemical equilibrium. We're going to find, though, guys, that trying to do this with my Wacom tablet has become a little bit interesting. So we may have some technical difficulties. We'll work through those as we go. So moving along then, as we get started today, there's actually two things that we're going to do. We're going to start by talking about the concept of equilibrium. We're going to do that by reviewing briefly the things that we've learned previously about acids and bases and conjugates. And then using that as a foundation, we're going to talk about the idea of equilibrium. Then once we're comfortable with the idea of equilibrium, we're then going to talk about Le Chatelier's principle, which you'll see is which is really the application of equilibrium that you'll need to be comfortable with. So in order to do this, we are actually going to start by reviewing some things about acids and bases and conjugates. So as you're working along at home, let's take a second and let's talk and let's review. So talking about acids and bases and conjugates, what I'd like to do is introduce this to you by starting a little differently. So in your notes, if you would, on the left here, we've got H2CO3 plus NH3, and then we have our yields arrow. And if you'd like to write those down with me, this will give you the opportunity to make sure that you're up to speed with what we're doing with this concept of acids and bases. So in the homework that you turned in previously, what we did is we gave you the products of this reaction and then had you identify which is the acid, which is the base, and which is the conjugate. Now we're going to do something a little bit different this time. Instead of that, we're going to tell you now that the acid is H2CO3 and the base is NH3. And with that information, you should be able then to predict the products and then figure out which is the conjugate acid and the conjugate base. So if you'd like to pause the video now and take a second and do that work, figuring out what your products are, given what you understand that acids and bases do, and then identifying which is your conjugate acid and which is your conjugate base. Go ahead and hit pause, do that work, and then when you're ready to move on and check your answers, hit play again. So now that you've had a second to work through this, let's talk about the theory behind what's going on. We may find that my presentation is going to freak out a little bit. Let's see what happens. Yep. So if we do that, and then if we come back now, I'm hoping, okay, that I can write. So what we know right now is that H2CO3 is the acid and NH3 is the base. And if we remember by definition, acids give away protons, hydrogen ions, and bases take in protons, hydrogen ions. So based on that idea, in order to figure out what our products are, we'll go to our acid, which is H2CO3, and we'll simply remove a hydrogen. And when we do that, our product is HCO3, and remember the charge becomes minus because that proton is positive. Now, where did that proton go? Well, the answer is the proton went to the NH3, and when that happens, our other product then is NH4, But remember, the NH4 becomes positive because the NH4 takes in that positive proton, and we end up with NH4 plus. So with that in mind, let's go ahead and, rather than do this in my handwriting, let's fly in those two answers. And then let's talk about which is the conjugate acid and which is the conjugate base. And if you remember what you learned from last time, the easiest way to identify your conjugate is to go to the acid. I'm going to switch colors. Go to the acid, remove the hydrogen. What is left then is the conjugate other, making that the conjugate base. So your HCO3 would be the conjugate base, and then of course the NH4 would have to be your conjugate acid. Now guys, this brings up a really interesting question. What does that mean to be a conjugate? We understand that conjugate means to form, so these are the acids and bases that are formed by these reactions, but the question then becomes, what does it mean to be a conjugate? Is it actually a base, and is it actually an acid, or is it something different than that? And the answer is no, these are actually bases and acids. So this conjugate base is fully a base, and this conjugate acid is fully an acid, and they can function as acids and bases. Now remember, the idea is that acids give away hydrogens and bases take in hydrogens. So now when these products, our conjugates, function as acids and bases, which they are, some of you are actually probably picking up on what happens. So when NH4 functions as an acid, it loses a hydrogen and turns into NH3. And when the conjugate base, HCO3, picks up that hydrogen, functioning as a base, it turns back into H2CO3. And guys, this is exactly what takes place in this reaction. These conjugate acids and conjugate bases actually function as acids and bases, and when they do, the reaction goes backwards all the while it's going forwards. So the acid and base form the conjugates. Just a moment. The acid and base form the conjugates, then the conjugates turn back into the acid and base, and this reaction starts going around and around and around and around, and it never stops. And guys, this is a concept that you've never been introduced to before. So what I'd like to do is I'd like to take a minute and show you how we represent this, and then I'd like to share some terms that we use when we describe this idea of reactions where the products turn back into reactants. So the way that we represent this is we simply use a double-headed arrow. And obviously that means that the reaction is going forward and backward at the same time. Now, the interesting question becomes, when does this reaction end? And the answer is, it doesn't. And that means we need to think about some new ways to talk about this idea. So going back to your notes then, let's talk about some terms that we use to describe this phenomenon. So the first term that you need to know is the term quantitative reaction. Guys, quantitative reactions are the reactions that you've been accustomed to thinking about up until this time. These are reactions that go to completion. They end when we run out of the limiting reactant. And so up until this day, all of the reactions that you've experienced in our class have actually been quantitative reactions, meaning that they consume the entire quantity of one of the reactants. That's the limiting reactant. When it's gone, the reaction's over. Well, guys, now we can talk about this other type of reaction called a reversible reaction. And in a reversible reaction, we have a reaction just like we saw before where the products turn back into reactants, all the while the reactants forming products. So it goes forward and backward, reactant to product, but products are turning back into reactants. And these reactions never go to equilibrium. They never go to completion. So if they don't go to completion, where do they go? And the answer is equilibrium. And equilibrium, this is the tie to what we learned last time. Equilibrium is the condition where the forward and reverse reactions happen at the same rate. Now, guys, when we bring up this term rate, the thing that's neat about this is we know a bunch of stuff about rate based upon the stuff that we learned last time. So remember what we know about rate. We know that rate is a speed of reaction, and we know that rate is dependent upon four things. It's dependent upon concentration, temperature, and surface area. But then remember, there's a fourth thing that reaction rates are based on, dependent upon, and that's a catalyst. Now, guys, catalysts do not come into the conversation of rate when we're talking about equilibrium. So we are going to be focusing on these four ideas: concentration, temperature, and surface area, and what that has to do with equilibrium. So again, in a quick review, up until now, we've only been talking about reactions that end. We are now going to talk about what are called reversible reactions that undo themselves. The products turn back into reactants. These never end. Instead, they go to equilibrium. Equilibrium is the condition where the forward and reverse rates are happening at the same time. And remember that rate is dependent upon concentration, temperature, and surface area. Okay, so moving forward then, how do we understand this idea of equilibrium? What does it look like when a reaction is moving forward and reverse at the same rate, at the same speed? Well, what we're going to do is we're going to look at a demonstration that's actually a YouTube video, much like the one that we normally use in class. Now, in order to understand how the demonstration works, you need to understand what the pieces represent. So you're going to see two things in this demonstration. The first thing that you're going to see is an amount of water in a bin. This water, in this case, is green. This represents the concentration of the reactants or the products. Now, the idea is, remember, concentration is measured in the units of molarity. So the more water there is in the bin, the more highly concentrated whatever that substance is, whether it's a reactant or a product. Now, guys, this may get a little confusing, but just stick with me. The other thing that you're going to see is a beaker. Now, this beaker is going to represent temperature and surface area. And it's not critical that you completely understand what that means. Just understand that the size of the beaker represents a reaction sensitivity to temperature and surface area. So again, concentration is the amount of water in the bin, and then temperature and surface area is represented by the size of the beaker. Now, with that said, here's what you're going to see in the demonstration. You're going to see first a couple bins. On the left, you're going to see the reactant bin. On the right, you're going to see the product bin. So this is a reaction that reaches equilibrium. Well, guys, what if this wasn't a reaction that reaches equilibrium? Well, if that's the case, then what would happen is we could just take the reactants and pour it into products, and when the reactants are all gone and when they all become products, the reaction is over. The reactant that we run out of first is called the limiting reactant, and that would be a quantitative reaction. Well, guys, that's not what you're going to see in this demonstration. In this demonstration, what you're going to see is this. The demonstrator is going to have two beakers. These beakers are of the same size. Oops, that wasn't a very good circle. These beakers are of the same size. And so what's going to happen is they are initially going to use one beaker to pour reactants into products. But then the other beaker is going to be used to pour the products back into reactants. Now notice initially, we don't have any products over here in the product side because none has been made yet. So initially, we are not going to have any product inside this beaker to turn back into reactants. But quickly that's going to change, because as we pour some into here, we're going to end up with some products, and then we can move that backwards. Now the question is, what is eventually going to happen as we start moving water from the left to the right and water from the right to the left using these two beakers? So what I'd like you to do, if you would, is pause the video and just give it some thought. What do you think is going to happen if we start moving these this water forward and backward using these two beakers? So pause the video, take a second to think about it, and then we'll come back and find out. So now that you've had the opportunity to think about what you thought was going to happen, we're going to actually grab this demonstration and we're going to take a look at this. So to do this, again, we'd like to thank Kevin Dirksen at Egan High School for providing this video. And it looks like this. So hopefully we can go full screen with this. And let's take a peek at what happens as we start using these beakers to move these substances from one bin to the other.
Okay, this little demonstration kind of helps us with the idea of equilibrium and reversible reactions. So what we see here, to start off, we have colored water, some green water here, that represents our reactant side of our process. And then, of course, we have our empty container over here that represents our product side of the process. So in any good reaction, when you start the process, everything's a reactant. So we all have all the water over here, and nothing is a product. When you have a reversible reaction, or a reaction that has to reach equilibrium, what happens is as soon as you start making product, that product also starts making reactant. So on the very first scoop, if I'm using two identical beakers, if I go in here and scoop, on the very first scoop, all of it is going to be reactant turning into product, and none of the other. However, the very next time I scoop, some of my product is actually going to go back into my reactant side. Now, if I continue to scoop like this and continue to do this, you'll notice how at first the reaction ran really fast. And at first, a lot of water was switching sides going to the product side. But then it kind of seems to slow down a little bit. And at some point, if I continue to scoop, the amount that I scoop going each direction will become the same. So if I look, I have 250 milliliters here, and I only have 200 on this one, so I'm not quite there yet. Okay. So now if I have 250 milliliters here, I have 225, so I'm getting closer. So I'm almost at equilibrium. And here I have 225, 225. So if we look, and again, this is not perfect measurements, but if we look at our volumes there, they're almost identical, which showing that the amount that's crossing from here to here is equal to the amount going this way. Now, the amount in the beakers represents the rate. Okay, so the rate of transfer is the same. From here on out, I can do this for a day, 2 days, 10 days, 10 seconds. It doesn't matter. This is at equilibrium. Okay, so the amount I take from here goes here, the amount I take from here goes here, and that process will never end. So this reaction now is basically over. It doesn't mean it doesn't keep reacting. It just means it's not going to change anymore. So we've reached equilibrium. Okay?
Okay, so guys, hopefully as a result of watching that video, it reinforced the idea that equilibrium is this interesting condition where the forward and reverse reactions are happening at the same rate. So let's take a look and let's break this down and let's make sure we understand what's going on. So we actually have two volumes, if you will, represented in this diagram. You'll notice that we've got the volumes of water in these beakers. And this represents the rate of the reaction. The amount moving forward is equal to the amount moving backwards. And so the forward and reverse rates are equal. And that's the definition of equilibrium. But then you'll notice that back here, we also can talk about the amount of water that is in the bins. And you'll notice that the amount of water in the bins is no longer changing. Because the amount that's moving forward and backward is equal, the amounts that are in these bins stop changing. So this height and this height no longer changes because the forward and reverse reactions are happening at the same rate. Now remember that the amounts inside the bin represent concentration. So we have the concentration of the reactants, we have the concentration of the products, and you'll notice that these are unchanging. But the other thing that you'll notice is that they're actually equal. Now here's the thing that's interesting. So now we've got two things that are equal. We've got the forward and reverse rates that are equal, but we've also got the concentrations which are equal. Now, here's the thing that's interesting, guys. In order to be at equilibrium, the rates have got to be equal, but the concentrations do not need to be equal. And so I'd like to show you an example of that. But before we move on, let's make sure we're clear. We are now at equilibrium. We know that because the forward and reverse rates are canceling each other out. The concentrations, represented by the amounts in the bins, are unchanging. And that will always be true. But they're also, in this example, not just unchanging. Oops, just a second. They're not just unchanging. Sorry about the technical stuff. They're also equal. But that doesn't have to be the case. So the question is, how could we change this demonstration in such a way that our rates are still equal, but our volumes inside the bins are unchanging, but not equal? What could we do to run this experiment again and make that the case? And maybe you realize that the thing that we can do is run this experiment again with different size beakers. So this is actually what's going on. We've talked about this reaction, and we've understood that this is an actual example of a reaction that is an equilibrium process. It goes forward and back. Now, guys, when this reaction actually takes place, it turns out that the forward reaction has a larger sensitivity to temperature and surface area, and the reverse reaction has a smaller sensitivity to temperature and surface area. We're going to represent that with a bigger beaker and a smaller beaker, and now we're going to run this demonstration again. So what does that look like? Well, it's going to look like this. And notice this time we've reset the scales. We have all reactant, no product because we haven't started yet. But now notice our forward reaction is going to carry out through a big beaker, but our reverse reaction is going to be carried out through a smaller beaker. The question is, how will this change the outcome of this demonstration? Pause the video and think about that for a second. Okay, welcome back. Let's actually grab this other video and take a look and see at how this changes the situation. So here we go. You'll notice now that we've got all of the reactants on the left. He'll put the products bin down in just a moment, and we're going to pick up from here.
If we reset our setup here and we begin again, but this time, instead of having equal amounts, we have very unequal amounts, where I'll again use the big beaker as reactant. I'm going to use the little guy for my product set. Okay, so in our very first scoop, again, it's all reactant, no product. Again, I start scooping and I get some product back to reactant. Okay. Now you might think there's no way you can get equilibrium here because the big scooper will always outdo the little guy, which is kind of a common thought. But the reality is that doesn't happen. At some point, the big one actually does run out of steam here. Again, we're looking for equal rate of transfer. So if I check, okay, I'm doing 140 milliliters here, and here, again, I'm at about 140 milliliters. So if you look, these two volumes, even though they're in different size containers, again, are showing almost identical volume, which means if I pour 140 into here, and I pour 140 into here, there's no difference, okay? So I am now at equilibrium, okay? So switching again, I can do this all day long, and from this point on, there will be no change in the volume in either tub, which means this reaction from reactant side to product side is at equilibrium. Okay, I can just keep right on doing it and nothing changes here. Again, we have 140 plus. This particular scoop happens to be actually less in terms of what we have. Okay, it's not perfect with using scooping water. But again, we see 150 to 140, same amount of volume crossing over equilibrium. Okay, now in this case, if we look, we had equilibrium, so the process is at equilibrium. But if we look on the product side, we have much more water than we do on the reactant side. Okay, so in this case, because we end up with more product, we would call this a product favored equilibrium. We have less reactant, so it is not reactant favored. Okay.
And there we have it. We can see now that we are still at equilibrium because the amount of water moving forward and backward is the same, but this equilibrium did not create equal volumes. So let's capture a still here. This may freak out. Let's see what happens. Yep, it did. So let's capture this still here and let's talk a little bit about what we're looking at. So if you remember, we came to this point, I believe he said there was 140 mils here and 140 mils here. So the amount that he's moving forward and backward are equal. You may remember that this amount of water represents the rate and the forward and reverse rates are equal. This is equilibrium. This represents equilibrium. But you'll notice as well, if we now look at the amount of water that is inside the, if we look at the amount of water that is inside the bins, notice he drew in these lines, these are not equal. So with the beakers, we were moving the same amount of water forward and backward. And as we were moving the same amount of water forward and backward, these amounts became constant, but not equal. So at equilibrium, the forward rate and the reverse rate are equal, and you'll notice that these volumes, which represent concentration, are not equal, but they are constant. So as he said, he could go on and do this forever and ever and ever, and this amount of water and this amount of water would not change. So the concentrations don't change. They're constant, but they're not the same. So what is equal? The rates are equal. These forward and reverse processes are undoing each other, and the concentrations are constant. Now, guys, before we move forward then and talk a little bit about what we're going to do with these ideas, we want to foreshadow here for just a minute. So I made a measurement. It's an estimate, but this height is about 70 millimeters, and this height is about 30 millimeters. So our products are about 70 high, and our reactants are about 30 high. Now, guys, the reason that we bring this up is because remember, these heights, these amounts are not going to change. They are literally a constant. And you're going to find out in the next class period that this constant has a name. And I'd like to share that with you. Don't get too caught up in this. We'll come back to it later. But this amount, 70-30, actually has a name. This product to reactant ratio, which is 70 divided by 30, or 7:3, or 2.3, is what is called the equilibrium constant. And this equilibrium constant, which is abbreviated Kc, is the amount of product divided by the amount of reactant at equilibrium. And you'll notice that in this example, it's 7:3. And this number, this equilibrium constant, is a constant. Remember, the idea here, guys, is that we could continue to do this reaction. This is probably going to wig out. Oh, it didn't. We could continue to do this reaction over and over and over, and the forward and reverse processes will just continue to undo each other. This 70-30, or 7 divided by, which is 2.3, sorry, which is 2.3, this doesn't change. It really is a constant. And you'll see that these values, these molarity to molarity ratios, you can actually look up in books for real chemical reactions. Again, we'll talk more about that next time. So guys, now let's do this. Now that we understand at some level this idea of equilibrium, let's make sure we're really clear. So we understand from everything that we just talked about that we've got forward and reverse reactions, and that these things can reach this condition of equilibrium where the forward and reverse reactions are undoing each other. So let's be clear. When a system is at equilibrium, what's equal? Well, the answer are the forward and reverse rates. Remember the amount of water in the beakers. Now, at equilibrium then, what is true of the concentrations? Are they necessarily equal? And the answer is no. The concentrations are not necessarily equal, but they are constant or unchanging. And in the case of our little thing that we just did, that was 70 to 30, and that doesn't change. Now here's the question, what do we mean by that doesn't change? And this is where we get into the last thing we're going to talk about today, which is Le Chatelier's principle. So guys, Le Chatelier's principle is really interesting, and it goes like this. So we know that this is a 70 to 30 ratio, which is 2.3. Now, here's the thing that's interesting about Le Chatelier's principle. We know that if we continued to move these forward and back, that wouldn't change. But what about this? What if we came along and what if we dumped in a bunch more water into the product side of this reaction, and then we started scooping again? What would happen then? Well, here's the thing that's interesting. With those same beakers, if we started moving water forward and backwards again, now we've got a bunch of water over here that shouldn't be here. And so what would happen is a lot of this excess water would start moving backwards, and this side would start to fill up as well, and this side would start to go down. Now, you want to guess where that's going to stop? It will actually stop at that 7 to 3 ratio. Of course, it can't go back to 70 to 30 because we've got more water than we need, but it would go back to that same 2.3 to 1 ratio. And guys, it does not matter what we do. If we were to come in here and if we were to dump in a bunch of green water into this side, well, then that green water would move forward. Sorry, that's hard to see. Some of that green water would move forward. This would start to go down. This would start to go up, and it would come back to that 7 to 3 ratio. Now, what if we did something tricky, and what if we sucked some of this water out and made this go down? Well, if this went down, then what would happen is the reaction would actually try to replace it. This would move forward faster than this moved backwards because there'd be less to scoop backwards, and we'd still go back to that 7 to 3 ratio. So guys, fundamentally, here's the deal. It doesn't matter what we do to this reaction. We can add some here, we can add some here, we can remove some here, we can remove some here. This ratio will always go back to this 7 to 3 ratio. It truly is a constant. Now guys, the name of that phenomenon is actually what we call Le Chatelier's principle. It says this. It says equilibrium reactions will offset whatever changes are made to them to return to their equilibrium ratios. This allows us to make predictions in terms of which direction reactions will shift in order to get back to equilibrium. Now guys, sometimes this can be a little bit difficult to follow, so there's actually a saying that you can use to make this easier. It says, same side does the opposite, opposite side does the same. So let's go back again to our first example that we talked about here. So imagine that we came along and imagine that we dumped in a bunch of green water over here. So now we've got a bunch of extra green water over here. So this is the change we made. We added more green water. Now, here's the deal. Imagine that this is our equal sign. Okay, now here's what's going to happen. When we start scooping water again, some of this water on the right is going to get moved to the left. So we increase the amount of water on the right. So how does the reaction respond? Well, it takes that water on the right and it moves some of it to the left. So what does that do? Well, in response, this goes down and this goes up. So guys, look at what that says. Same side does the opposite, opposite side does the same. So if the change that we made was to make the right side go up, look at how it responds. Well, on this side of the reaction, the same stuff will do the opposite. Same side does the opposite. Same side does the opposite. This goes up, this is going to go down. But then notice what happens over here. The opposite side of the reaction does the same. So if the change that we made was to increase the right, as it goes back to equilibrium, the left will increase. So same side does the opposite, opposite side does the same. Now guys, understand that doesn't only work for water in bins, it also works for reactions. Now when we say same side does the opposite, opposite side does the same, we mean same and opposite side of the yields arrow. So let's take a look at this and see what we're talking about. So here we go. So imagine that we've got this reaction, and the change that we're going to make is we increase the amount of HF. So HF goes up. So what does that look like? Well, guys, think about it this way. HF goes up, looks like this. It's just like dumping water into that left side bucket. So how is this reaction going to respond to get back to balance? Well, the idea is over here on the left-hand side, we've got too much stuff. So what do those need to do to get back to balance? Well, they have got to go down. Well, what's got to happen to the stuff on the right to get back to balance? Well, they have got to go up. So notice what happened. If this is the change we made, the stuff on the same side did the opposite, the stuff on the opposite side did the same, and this then would return to equilibrium. Now here's the way we talk about this. The stuff on the right went up, so we say that this reaction shifts to the right. That simply means the stuff on the right goes up. Now, let's look at another example. Say that we reset the tables, and this time we take this reaction and we heat it up. Well, if we heat it up, now we have an imbalance like this. So now we need to return to equilibrium. So in order to come back to balance, the stuff on the right needs to go down, the stuff on the left needs to go up. So again, the idea is same side does the opposite, opposite side does the same. Now, which direction does the equilibrium shift? Well, it's always in the direction of the side that goes up, so this equilibrium shifts to the left. And that's the way we talk about these equilibrium processes. So guys, that's it. Those are the things that you need to understand moving forward with these ideas. You need to understand two important ideas. First of all, relative to equilibrium, you need to understand that when we talk about equilibrium, equilibrium is the condition where the forward and reverse rates are happening at the same speed. So at equilibrium, rate is equal. But at equilibrium, concentration is not equal, but it is constant. Then, guys, we can use this to make predictions using Le Chatelier's principle. The idea being same side does the opposite. Opposite side does the same. And as we think about that, we can use these arrows in order to make shifting predictions. So let's take a look at the homework then and figure out what this might look like. So going out to our homework, I'm going to close out of this and I'm going to grab our homework sheet. And let's take a look at the homework and make sure we're comfortable with what we're doing. So looking at the Le Chatelier's homework, we're going to grab a hold of the homework assignment here, and you'll notice that the first page gives us some equations, and we have the opportunity to think through this a little bit. So let me show you how to do this. So you'll notice that we've got this equation, NH3, and then N2H2, and heat as products. And you'll notice that the first change that we have is we are going to decrease N2. So this is the way to think about this. So what we're going to do is the change we're making is we're decreasing N2. So if we decrease N2, how is this reaction going to respond? Well, everything on the same side is going to do the opposite. So if you decrease N2, the same side of the reaction, in response, all of these are going to go up. So same side does the opposite, and then the opposite side does the same, so this goes down. So then transferring that over here to these answers, letter A, NH3 goes down, letter B, H2 goes up, and then letter C, temperature goes up. Now the question is, what direction does the equilibrium shift? The things on the right went up, so that would be a shift to the right. So let's try one more. So looking at our next example then, the example that we have now is we are going to increase temperature. So if temperature goes up, everything on the same side will do the opposite, down, down, and down. And then everything on the opposite side will do the same, so that will go up. And so then what is the effect on NH3? Well, NH3 is going to go up. What is the effect on N2? It will go down. What is the effect on H2? It will go down. Now, what direction did the equilibrium shift? Well, which side went up? Well, this side went up, so that would be a shift to the left. And you'll just continue on with the rest of those. Then, guys, moving on to the next pages, you'll notice that there are some descriptive things to think about relative to the demonstration that you saw. Please understand that the answers that we have provided actually were built around the demonstration that we do in class. So as you're reading the answers to the homework, where it talks in the homework about a graduated cylinder, that is actually the bin with the water in it. And when it talks about a glass tube, that is actually the beaker. So be thinking about that as you do the homework. Give this your best shot, and then if you need some help, make sure that you come and join your teacher during their question and answer session. Guys, thanks for your time. I hope that you're well, and let us know if there's anything we can do to support you. Have a great day.